Humanity has benefited much from space exploration. However, several aspects make this task challenging. One of them is the radiation environment. Ionizing radiation's effects in space can have a significant technological influence on spacecraft instrumentation, aside from the life-threatening hazards it poses to humans. Therefore, its modeling and monitoring is crucial. Earth's radiation environment has been widely researched, but the same cannot be said about the Jovian system, composed of Jupiter, its moons, and rings. But why investigate the Jovian system in the first place? Galileo, a previous mission dedicated to investigate Jupiter, provided strong evidence of the existence of oceans beneath the icy crust of Jupiter's moons, Europa, Ganymede, and Callisto. As a result, these icy roads were hypothesized to be possible habitable zones. To study these moons, ESA will launch in April 2023 the JUICE mission, planned to have almost 8 years of interplanetary cruise and a tour of 3.5 years of the Jovian system. The spacecraft will perform several flybys of the moons, but Ganymede will have a special attention as it is the only moon in the solar system to have an intrinsic magnetic field. Among the JUICE spacecraft instruments, there is RADEM. Both as an housekeeping instrument and as a charged particle spectrometer, it will detect electrons, protons, and to some extent ions within certain energy ranges. RADEM will collect measurements of the Jovian radiation environment from 3 main sources: solar particle events, which are sporadic bursts of charged particles accelerated either by coronal mass ejections or solar flares; galactic cosmic rays, which is a low, uniform flux mainly composed of protons in a huge range of possible energies; and lastly, trapped particles contained in Jupiter's magnetosphere. The stronger a planet's magnetic field is, the bigger its influence area, or magnetosphere, will be. This allows for the containment of more energetic particles. Jupiter's surface field magnitudes can be up to 20 times greater than Earth's, and, as a result, Jupiter's trapped particles will be much more energetic than the ones present on Earth. To understand the dynamics and origins of these particles, 2 quantities are needed to be measured: the particle energy spectrum and the pitch angle distribution. To measure the energy spectrum of protons, electrons, and heavy ions, RADEM has 3 different detector heads based on silicon stack detectors. A silicon stack detector is composed of silicon sensors interleaved by absorbers. From the distance that a particle travels in the stack and the energy that it deposits on the sensors, its incident energy is identified. To measure the pitch angle distribution, the angle between the particle's direction and the local magnetic field, the directionality detector head was developed. Composed of a toroidal copper collimator with 28 apertures, it will give information about 4 different directions, each direction with 9 different azimuthal angles. RADEM will therefore be the focus of my master thesis project, and, with the supervision of Patricia Gonçalves and Marco Pinto, I will characterize RADEM, establish the detection settings for launch, and analyze the first data collected during the commissioning phase.